So we have defined last time as the acceleration of a particle in a velocity field, and we have seen that we can write the total derivative of velocity as decomposed into convective acceleration and local acceleration. And if you remember, this was the final formulation we did. Okay. Now we will apply this in different types of coordinates. So we will express the acceleration in Cartesian coordinates and in polar coordinates. Okay, so this vectorial relation can be decomposed into x, y, and z. All you have to do here, for example, in Cartesian coordinates, to get APX, you just have to replace v vector by its x component, which is u. So you will get that AX is u del u by del x plus v del small v by del y plus v times del u by del y plus w times del u by del z. Okay, plus here del u by del t. This will give you the x component of acceleration. To get the y component, all you have to do then is to replace v vector here. Instead of u in these locations, you will put small v. And to get a z, instead of u replacing the component of velocity vector, you put w. So you will end up with the following relations, that AX can be calculated as in Cartesian coordinates as u del u by del x plus v del u by del y plus w del u by del z plus del u by del t. It's the same for AY and AZ. Now, as we did in XYZ coordinate system, we can also express acceleration in cylindrical coordinates, and these are the expressions for acceleration along AR, along U theta, and along Z. Okay. Now, of course, you don't have to memorize these formulas. I'll provide you with the formula sheet summarizing all formulas you are responsible for. Okay. Now, for the exam, you'll just have the part until continuity. Okay. Let us do an example on acceleration. We consider a two-dimensional steady incompressible flow through the plane converging channel shown. The velocity on the horizontal center line x-axis is given by v vector equals to v1 times 1 plus x over L times I. Find an expression for the acceleration of a particle moving along the center line using first the Eulerian approach and then the Lagrangian approach, and evaluate the acceleration of the particles at the beginning and at the end of the channel. Okay, so first, let us remember what is the difference between Eulerian and Lagrangian approach. Whenever we talk about Eulerian approach, this means that we define a fluid domain and we express the velocity field at a certain position. Okay, so we express the velocity field function of position and time. So this is the Eulerian approach. So I can ask for the velocity at any position. All I have to do is to replace in the equation of velocity at the corresponding time. And if it's a steady state application, when we say steady state, this means at a certain position, the velocity is not changing with time. So in this example, the velocity field is given by the following relation. V is equal to a certain constant v1 times 1 plus x over Li on x-axis. So velocities here are just restricted to x direction. And as you can predict here, you have, because of the flow is incompressible, okay? Then you have m dot n is equal to m dot out, and m dot is the same at any cross section. So any cross section I consider will involve the same mass flow rate m dot. And since m dot is constant, and we know that m dot is proportional to both a and v, so when here in this system, what will happen is that since I have a converging channel, A is decreasing as x increases. Okay, so as x increases, A decreases. What will happen for the velocity? The velocity will increase because m dot can be written as rho times A times V. So since m dot is rho AV and the flow is incompressible, so rho is constant, then if A will decrease, V should increase to conserve mass. Okay, so, and this is the expression which will give me the increase of velocity with x. And as I can see, it's a linear increase. Now, when we talk about first to get the acceleration using the Eulerian approach, all I have to do is to apply the definition that in Eulerian approach, to get the acceleration, I should account for the total derivative of velocity, and I should add local acceleration to convective acceleration. Okay, so let us go back to the definition of acceleration. Then I have the following. We have defined together that the acceleration of a particle is given by dv by dt, which is equal to u del v vector by del x, plus v del v vector by del y, plus w del v vector by del z, plus del v by del t. Now, if we look at the expression of velocity, the velocity is independent of time, so this term will cancel out. Also, as we can see here, the velocity is restricted only to a component along I, so we only have u component, and v component is 0, and w component is 0. So since we don't have a flow along y and z, no acceleration along y and z. And if you replace in ay, az, since v and w are always equal to 0, this will give us that ay is 0, because all terms include small v, and az is 0 because all terms of az includes w. So we just have to compute ax to get the acceleration of the particle. Okay, so to get ax, we just have to say that ax is u del u by del x plus v del u by del y plus w del u by del z. But since v and w are 0, these terms, so this is 0 and this is 0. So in this example, the acceleration along x is restricted to u del u by del x. So all I have to do is to compute what is del u by del x. This is u. U is the component along I. Okay. If you derive u with respect to x, you have del u by del x will equal here to 1 is a constant, okay, and you have v1 times x over l. The derivative is v1 over l. So del u by del x is v1 over l, and u is, so to get ax, I should multiply by u. So I get that ax is v1 squared over l times 1 plus x over x. So as I can see here, also, I have acceleration of the fluid with increase of x. And this type of acceleration is called convective acceleration. This is related to location. So the particle is accelerating with location. In the flow field domain, I have acceleration with position, not with time. Because if I observe one fixed location, the velocity is not changing. So if I consider any point and I observe it at any time, I will get the same velocity. This is why I don't have here a local acceleration. I just have a convective acceleration related to change in x position. Okay. Now, they want me to get the acceleration using another procedure, using the Lagrangian procedure. The Lagrangian procedure consists of what? Consists of following a particle with time, okay, and writing x function of time, and then deriving x function of time to get velocity, to get u component, and then deriving u component to get a. This is the way you are used to do in dynamics, okay? And we'll verify together that at the end, we'll obtain the same result, Okay, let us see. So first here to say, to use Lagrangian approach, I need to define x of the particle, function of time. How to do this? I should go back to the definition of the velocity. We know that by definition, u is dx by dt. U is the component of velocity along x, so it's the derivative of the position of the particle with respect to time. And if I replace u by its expression, I will get a differential equation of x and time. So what I can do here, I can separate variables and integrate from both sides. I integrate one side with respect to x and the other side with respect to time. Okay, so let us see how to do this. So as we said, we have that A is, so first, for the Lagrangian approach, we know that U is dx by dt, okay? And then A is the derivative of velocity with respect to time. So first, we need to get x function of time, as we said. Now, to get x function of time, we'll use the differential equation that U is dx by dt, okay? Now, we need boundary conditions to do the integral procedure. So we can consider that at t equals 0, we will consider the particle which was at x equals 0 at t equals 0, okay? And want to find the equation of motion of this particle. So what we should do is, after separating variables, so from this side, the variable is x of the particle. From the other side, the variable is time. So now we integrate the boundary condition. We considered that at t equals 0, x equals 0. And we will integrate from 0 to any time t to derive the expression of x of particle p. Okay, so now from the first side, the integral of this function is L ln 1 plus x over L. And from this side, the integral is v1, because v is a constant, v1 times t. Okay, so in this way, we were able to get an expression for x of particle, function of time. And now, using the Lagrangian approach, okay, we can say that knowing x function of time, we can get the expression of velocity of the particle, function of time, by doing dxp by dt. So deriving this expression with respect to time will give us v1 exponential v1t over L. And finally, to get the acceleration of the particle, we derive u with respect to time. So we get v1 squared over L exponential v1t over L. Now you will tell me, but the expressions are different. It's true that the expressions are different. Here we found a function of time. Before we found it function of x. But look, if you go back to your Lagrangian, to your Eulerian expression, and you replace x by this function of time, you will end up with this result. Okay, so both methods at the end will give you the same result, but one will give you a function of t, the other will give you a function of x. But x and t are related through the Lagrangian approach, because if I consider a particle moving in the fluid, I can relate the position of this particle with time. So if I just replace x particle by its expression of time in the expression of the Eulerian approach, I will get exactly the same result. Okay, because the two methods at the end will are consistent with each other and should give same results. And we can verify now that for the last question, they are asking to use these two different expressions to evaluate the acceleration when the particle is at x equals 0 and at x equal L. When we use the Eulerian approach, this question can be solved straightforward. Why? because in the Eulerian approach, we already expressed A directly, function of X. So all we have to do is to replace into the expression of A we got from Eulerian approach, X by 0 and X by N. So if you remember, this was your expression from Eulerian approach. So from Eulerian approach, we got that A is V1 squared over L times 1 plus X over L. So now if we replace X by 0, we get that at X equals 0, we have A equal to V1 squared over L. And for X, the second question was to determine for X equal L, what is the acceleration? For X equal L, L over L is 1. So we get 2 V1 squared over L. Now, if we want to use the Lagrangian approach to determine acceleration at these positions, we should first, since A is expressed function of time, we should first find at X equals 0, what was the corresponding time? And at X equal L, what is the corresponding time? To do this, all we have to do is to go to the equation of X function of time, okay? From this relation, we set for X equals 0, what was the time? The time T, okay? We can get what is the value of time T. T was 0, okay? And then we replace T by 0 here, and we get V1 squared over L, which is exactly the same result we got in the Eulerian approach. Now, for X equal to L, we do the same procedure. We replace here X by L. We find the value of T here, the corresponding value of T, and then we replace back in this relation to get the acceleration, and also obtain the same result. Okay, so this means that both methods, of course, will end up with the same result. So as you can see here, the corresponding time for xp equal to L is L over V1 ln of 2. Replacing into the expression of a function of time, we'll get back the same result, which is 2V1 squared over L. Okay. Any question on this? Okay. Now we will move to the definition of fluid rotation. Okay. You know that you have, like in dynamics, you have several types of motion. You have translation, you have rotation. Now for fluids also, you can have deformation. Okay. So let us consider here how to deal with fluid rotation. So let us consider, for example, a fluid particle. And this fluid particle is originally of this shape. So you have right angles. And because of combination of rotation and deformation, we end up with the following position of the particle at time delta t. Okay. So first, if we want to find, if we want to relate, if you want the rotation to angles, what can we do? We can say that here we have for this side, okay, for this side, the rotation is, the angle of rotation is delta alpha. For the other side, it's a different value. And here we are rotating counterclockwise, and we consider the counterclockwise as positive. So this side is rotating plus delta alpha. This side is rotating minus delta beta. So because we have different values, if you want to take an average, a value of rotation for the body, we can do the average value between the two, which is delta alpha minus delta beta over 2. So this is the average rotation of the body, the rotational component of the body. Okay. So the body first rotated by an angle of half delta alpha minus delta beta and was in this position. Now, this position of the particle is different from this one. So this is due to deformation. So if we want to know now what is the total deformation of each side, all we have to do is to say this side due to rotation was at this position, but due to deformation, it ended up at the following position with an angle here of delta beta. So in total, what is the total deformation angle? This is the total deformation angle equal to half delta alpha minus half delta beta plus delta beta. So in total, the deformation of this side is half delta alpha plus delta beta. We can do the same procedure for the other side. If we want to find the total deformation of this side, we say that this side, okay, was originally, due to rotation, was in this position, okay, and the final position of it is with an angle here equal to delta alpha here, okay. So then we can say that the deformation angle, so this is the whole angle is delta alpha. The deformation angle is this one, which is delta alpha minus half delta alpha plus half delta beta. So the deformation of this side is also equal to half delta alpha plus half delta beta. Okay, so we can conclude that the total angle of deformation here is delta alpha plus delta beta. And this is expected because, you know, deformation is the variation from the total variation of the angle. Here, the sides where you have 90 degrees sides. So now the new angle is equal to 90 minus delta alpha minus delta beta. So the total deformation is equal to delta alpha plus delta beta. Okay. So as we can see, the fluid behavior in rotation, we should define its angular velocity and we should define its deformation. Okay. Now, a fluid particle moving in a general three-dimensional flow field may rotate about all three coordinates. So here we just considered a certain particular case of rotation about one axis. But in general, the particle rotation can be done in different directions, and we can define the angular velocity as omega xi plus omega yj plus omega zk, where omega x represents the rotation about x-axis, omega y represents the rotation about y-axis, and omega z is the rotation about z-axis. Now, what we will do here, we'll define some if you want, new concepts, how to relate the rotation of a flow field, the angular velocity of a flow field to its velocity field. Okay. Now we are not responsible of the demonstration. It's a complex demonstration. Just you should know that here we are considering that the positive sense of rotation is given by the right-hand rule, and we can relate the angular velocity vector to the velocity field through the following mathematical operator. Okay, we can say that the angular velocity omega is half curl v. Okay, and curl v is a mathematical operator defined as follows, which is grad vectorial v, and it's defined as del w by del y minus del v by del z along I, plus del u by del z minus del w by del x along j, plus del v by del x minus del u by del y along k. So if I give you a velocity field v, and you know the values of u, v, and w, their functions, you can deduce if you have flow rotation or not by just doing this calculation. To have no rotation, omega should be 0. So to have omega 0, what is the condition? Should have all of these terms equal to 0. So in this case, del w over del y minus del v by del z should be 0. And also del u by del z minus del w by del x should be 0. And del v by del x minus del u by del y is 0. If any of these is not 0, this means that you have a certain rotation of your fluid. Okay. No. Rotation of fluid particles will always occur for flows in which we have shear stress. So in the majority of application, we have a fluid rotation because the majority of application includes shear stress. In cases we are dealing with regions that are far from walls where viscous effects are negligible, then we can have the case of no particle rotation. And in this case, we call the flow irrotation. Okay, so flows for which no particle rotation occurs are called irrotational flows. Now, although no real flow is truly irrotational because always you have a certain viscous effect, okay, it turns out that many flows can be successfully studied by assuming they are inviscid and irrotational because viscous effects are often negligible. Now, another important property of fluid that we can define is vorticity. Vorticity is a property which is equal to twice the rotation of angular velocity vector. So vorticity vector is 2w is equal to the curl of velocity. And the vorticity is a measure of the rotation of a fluid element as it moves into the fluid field. So it's directly related to the angular velocity. And higher is the vorticity, higher is the rotational effect. Now, as usual, we are always dealing with Cartesian coordinates and cylindrical coordinates. So we will also define the curl of velocity, which will give us the angular velocity in polar coordinates. And then from this definition, we can deduce the expression of vorticity in polar coordinates by just multiplying this by 2. Okay, so by multiplying omega by 2, because already curl V is directly the vorticity. Okay, while to get omega, I should do half of the curl V. Okay, so this expression will directly give you the vorticity vector. Okay, and you can deduce from it omega because this vorticity vector is equal to 2 omega. So omega can be defined as half of curl of velocity vector. So once you get this, you divide by 2 and you get omega. Okay. So all you have to do is just to apply these relations to know if you have rotation in your fluids or not. Now, another important concept to define in fluid rotation is the circulation parameter. Okay. And the circulation is a line integral of the tangential velocity component about any closed curve fixed in the flow. Okay, so we'll take an example of this. So circulation is defined as the integral over a closed curve in the flow of v dot ds. Okay, where ds is the streamline coordinate. So ds is an elemental vector tangent to the curve and having a length ds of the element of r. A positive sense corresponds to a counterclockwise path of integration around the curve. So always we perform our integral into positive direction. The positive direction is counterclockwise. Okay. Now, mainly used, this parameter, the circulation, is mainly used in the calculation of lift force around objects. So the importance of this parameter is that it can be used for force calculations. So for example, the lift force per unit depth can be defined as rho times the stream velocity times the circulation. Okay. Now, let us see how we can calculate circulation. So for example, we'll take a certain simple example to illustrate how circulation can be calculated. Okay, let us consider a simple case where you have a rectangular curve, okay, and you have the flow. In this case, the flow is defined as follows. You have along the side OA the velocity, you have u component of velocity, okay. Of course, look, at the end you are doing integral v dot ds. Okay, so even if you are not considering a certain streamline, but when you do v dot s, you just take the component of velocity along this line. So this means if your flow is defined by u and v, so you have a 2D flow in this case, okay? And you select any surface, any closed surface, and you want to calculate the corresponding value for circulation along this curved surface, okay? Then you should project, when you move on along the curve, you should do the dot product of velocity at this location dot ds. So then you will just take the component of velocity along the line you are moving on. So for example, when you move along OA, okay, this is your S. Then if your velocity has two components, u and v, you will just take the component that is along OA, which is the u component. So when you integrate over OA, you will use u component. When you integrate over AC, you will use v component of your velocity field. When you integrate over BC, you will use the u component along BC. And when you integrate over BO, you will take the velocity v component. Okay. Now, of course, the u and v are varying through your domain, but you can use Taylor expansion to say that if the velocity along OB is v, then the velocity along AC can be defined as v plus del v by del x delta x. And if the velocity along OA is u, then the velocity along BC is u plus del u by del y delta y. Okay? So now, by applying the formula of circulation, which is integral, so I will turn into the counterclockwise direction. So I will move like this, and I will do integral v dot ds. If I start by the first segment, okay, I have the velocity component along OA is u, and when I do delta s here, yani, when I do the integral from O to A, delta s is equal to delta x. Okay, so v dot ds will give me u dx, and by integrating over element OA, since u is constant over this distance, okay, so I will consider that because I'm considering a small element, okay, then I will consider that as the result will be, by taking u outside, it's u times delta x. So this is the first value I get. Okay. Now, I will move now along AC. When moving along AC, the velocity is v plus del v by del x delta x. Okay. And by projecting, so here I have that this is the component of velocity along AC. And by integrating over AC, so I have like v plus del v by del x times delta x dy. Okay, ds here is dy. So when I integrate over dy, so this is constant over y, I can take it outside of the integral. Integral over dy from point A to point C is delta y. So the second term will give me plus v plus del v by del x delta x times delta y. Okay. Now I will continue for the remaining segments along CB. Okay, along CB now I am integrating from C to B. So this will give me minus, because I'm moving in the negative x direction. Okay, so when you do the dot product, you will get minus u plus del u by del y delta y times dx. And when you integrate, sorry, you will get plus u plus del u by del y dx. But when you integrate, integral of delta of dx when you go from C to B is negative, which is minus delta x. Okay, so then you will get minus u plus del u by del y times del y delta x. And finally, the same for the for the final segment, you will get minus V delta Y. Okay? So in this case, we obtained the total circulation over this closed path. Okay? Over this closed path. So now, this expression, okay, will give us, in total, when we simplify terms, we will get that the circulation is del V by del X minus del U by del Y, delta X, delta Y. And if we go back to the definition of, for a 2D flow, okay, if you apply for a 2D flow the relation of angular velocity, you will see that this term represents 2WZ. Okay, let us remember how. Let us go back to this definition here. Okay, so how we define the velocity omega from this relation? Okay, this is the general definition of omega. If you have a 2D flow where you only have U and V, and you don't have W, W is 0, what will happen? In this expression, okay, you have that this term, every term containing W will cancel out, okay? So you don't have, this term will be 0, and this term will be 0. And since you don't have motion along Z, so you don't have variation with Z. So del V by del Z is 0, and del U by del Z is 0. So you end up in this case, for a 2D flow, the value of omega is just half K times del V by del X minus del U by del X. So what can you deduce? That this component, del V by del X minus del U by del Y, is 2 times omega Z. Okay? So from here, we can demonstrate that for the case of a 2D flow, the circulation can be computed as 2 omega Z times delta X, delta Y. And delta X, delta Y represents what? Represents the area closed by the surface. Okay, so we can extrapolate this result to say that for a 2D curve, for a 2D closed curve, we can write that the circulation is integral over the curve of V dot ds equal to integral over the area of 2 omega Z dA. Okay, and we know that 2 omega Z is equal to the curl of V along Z. Okay, so this is another way. So this is the first way to calculate the circulation, and this is another way to calculate. Okay, now we'll do a small example to understand more these concepts. Okay, so we have a flow field with tangential motion where VR is 0 and V theta is only function of R. And we want to find first the rotation, vorticity, and circulation for rigid body motion. Okay, so when we say, in general, when we say rigid body motion, we can directly say, okay, that we can define that the velocity V is equal to omega times R. Okay, so in this case, the tangential velocity, which is here V theta, is equal to omega times. Okay, now let us see how to use this result to calculate the rotation, vorticity, and circulation. So to start with, the vorticity is related to the rotation by 2 omega, and omega is related to the curl of velocity. Okay, so since, what do we know about velocity here? We know that VR equal to 0, and only V theta is only function of R. And for rigid body motion, this means that we can use the relation V theta equals to omega times r. So since we are working in polar coordinates, first we go to our formula sheet and we search for the expression of vorticity in polar coordinates. Okay? And in this case here, we have a 2D flow. So Vz is 0. So if you replace Vz by 0 into the equation of polar coordinates, you will get first this general relation. So this is the vorticity relation